Welcome to our unit over electrons and atoms. A calculator and your reference chart will be useful as you watch this video and take notes. In the early 20th century, a new atomic model evolved as a result of investigations into the absorption and emission of light by matter. These studies revealed a relationship between light and an atom's electrons. This new understanding led directly to a revolutionary view of the nature of energy, matter, and atomic structure. We will start by taking a look at the properties of light. Light can behave as waves or as particles. Let's look at the wave nature of light. Light can travel through space as a wave. Waves have three primary characteristics. The wavelength, lambda, is the symbol, the frequency v, and the speed c. Wavelength is the distance between corresponding points on adjacent waves. The unit for wavelength is a distance unit. The symbol is lambda, and it is measured in meters. So the wavelength could go from a crest to another crest. The crest is the highest point in the wave, or it could go from a trough to another trough. The trough is the lowest point in a wave. The frequency v is the number of wave cycles or successive crests or troughs that pass a given point per unit time. The symbol is v, and it is measured in cycles per second. The unit can be the hertz, or it could be second to the power of -1, or 1 over seconds. All these units are equivalent, and you need to be familiar with all of them. The diagram here shows a wave with high frequency at the top, where you can see that the wavelength is very short, and a wave with low frequency at the bottom, where you can see that the wavelength is much longer. The speed of light, c, is a constant for all forms of light or electromagnetic radiation. The symbol is c, and it is 3.00 times 10 to the 8 meters per second. This will be given to you on your formula chart, so you do not have to memorize it. Let's look at the electromagnetic spectrum. Visible light is a kind of electromagnetic radiation, which is a form of energy that exhibits wave-like behavior as it travels through space. There are other kinds of electromagnetic radiation, and these include gamma rays, X-rays, ultraviolet and infrared light, microwaves, and radio waves. Together, they all form the electromagnetic spectrum. This chart down here will be given to you, so you do not have to memorize it. You can take a look at the chart and see that as we have a high frequency wave on the gamma ray side, the wavelength is very short. On the other hand, where we have a low frequency wave on the radio wave side, the wavelength is very long. So here we have increasing frequency towards gamma rays, and down we have the increasing wavelength towards the radio wave. So we can see that wavelength and frequency have an inverse relationship. Note also that all these forms of electromagnetic radiation will travel at exactly the same speed, which is the speed of light, 3.00 times 10 to the 8 meters per second. The speed of light, c, the wavelength, and the frequency are related by the formula speed of light equals wavelength times frequency, or c equals lambda times v. The frequency and the wavelength have an inverse relationship, as we discussed in the previous slide. Let's do an example calculation. What is the frequency of radiation with a wavelength of 1.82 times 10 to the -2 meters? So we start with our equation. C equals lambda times V. So we plug in numbers. 3.00 times 10 to the 8 is C, equals lambda, which is the wavelength. So 1.82 times 10 to the -2 multiplied by the frequency. I divide by 1.82 times 10 to the -2 on both sides. And I get that my frequency equals 1.65 times 10 to the power of 10 hertz, or second minus 1 would be another acceptable unit, or 1 over seconds. And the sig figs are correct. What part of the electromagnetic spectrum does this radiation fall in? So I go and look for my wavelength, which is in the 10 to the negative 2 range. So I go find that on my electromagnetic spectrum. There is 10 to the negative 2, and that falls in the microwave range. So it is microwave. Let's look at the particle nature of light. Not all properties of light can be explained by the wave model. So Max Planck and Albert Einstein refined our understanding of light to include its particle nature. Light can be described as a stream of particles or bundles of energy called photons. The details of the particle nature of light cannot be discussed in this class, but we will highlight the relationship between energy and frequency of light. So Planck and Einstein proposed the following relationship. The energy of a photon of light and its frequency are related by the formula energy equal Planck's constant times the frequency. And there is the formula over here. E is the symbol for energy. H is the Planck's constant, which is 6.626 times 10 to the negative 34 joules second. Again, this is given to you on your formula chart, so you do not have to memorize it. The unit for energy is joules. Energy and frequency, note, have a direct relationship. When energy goes up, the frequency goes up, and vice versa. Let's practice. How much energy does a photon of light with frequency of 4.2 times 10 to the 4 hertz have? So we write our equation. E equals h times v, or Planck's constant times frequency. So E, which is the energy, equals 6.626 times 10 to the negative 34 times the frequency, 4.2 times 10 to the 4. We just plug in our calculator, and that gives us 2.8 times 10 to the negative 29. And the unit for energy is joules. This is the correct sig figs. What part of the electromagnetic spectrum? So again, I have a frequency of 10 to the power of 4 range. So I go to my electromagnetic spectrum and find that. That one is on the top. Here is 10 to the power of 4. So this falls into the radio waves. We don't yet have a relationship between energy and wavelength, but we can combine the two previous equations and get the equation E is energy equals h, Planck's constant, times c, speed of light, over lambda, the wavelength. So let's practice an example. How much energy does a photon of light with wavelength 6.25 times 10 to the negative 14 meters have? So I have my equation again, E equals hc over lambda. So I just plug in numbers. H is 6.626 times 10 to the negative 34 multiplied by c, which is 3.00 times 10 to the 8, divided by lambda, which is the wavelength. So 6.25 times 10 to the negative 14. And that gives me 3.18 times 10 to the negative 12. And again, the unit for energy is joules. Atoms will absorb and then emit energy in the form of light when they are excited by any source of energy. This light is emitted in very specific patterns to each individual element, as you can see on the picture on the right. And because of this, emission spectra are a great tool to identify elements. Those emission spectra also match the movement of electrons between energy levels in atoms. So when electrons absorb energy, they do this in the form of small individual whole number packets, and these are called quanta. A quantum of energy is the minimum amount of energy required to move an electron from a lower energy level to a higher energy level. And a higher energy level is called an excited state. When an excited electron falls back to a lower energy level, light, and therefore electromagnetic radiation, is emitted in the form of photons. The lowest possible energy level an electron can occupy in an atom is called its ground state energy level. Scientists had established the dual wave particle nature of light, so they wanted to establish if electrons, which were thought of as particles then, could also maybe have the same dual wave particle nature. Sure enough, they did just that, and this led to the current quantum mechanical model of the atom instead of the Bohr model. So the discovery of the dual wave particle nature of electrons led to the Heisenberg uncertainty principle, and this states that it is impossible to determine simultaneously both the position and the velocity of an electron. So the exact position of an electron can never actually be determined. If you look at the Bohr model, it used to place electrons in exact locations or orbits around the nucleus. And this definitely contradicts the Heisenberg uncertainty principle. In the current quantum mechanical model, an orbital in the electron cloud represents a region, not an exact position. That is a probable location of an electron. And this is in line with the Heisenberg uncertainty principle, so the quantum mechanical model is the current accepted model of the atom. This concludes video 1. I hope you have taken good notes. Come to class prepared.